Welcome back. So, we were looking at the properties of steam. Essentially, we are looking at two phase mixtures. We looked at the PV and TV diagrams. We also looked at the phase diagram, the PT diagram, and saw the distinctions or the phase boundaries between, say, solid and liquid, liquid and vapor, and solid and vapor. So, now we will go back to looking at water, especially of mixtures of liquid water and steam, because as we discussed earlier, those are used a lot in applications like, say, steam turbines, and the same principles are also used where we look at, say, mixtures of refrigerant, liquid and vapor in, say, refrigerators and so on. So, we have a few things which we would like to define in that context. So, over here, let us say you have a container of containing both liquid and vapor of a substance. It is closed for some reason. We are not able to see the left boundary of this image here, but let us say you have a closed container with liquid and vapor, both of which are at equilibrium. Let us say the mass of the vapor is shown like this and the mass of the liquid is like this. So, what we know is that the total mass of what is there inside, so our system is essentially this. So, the total mass of the system is the mass of this mixture of liquid and vapor. So, it is the mass of vapor plus the mass of liquid. What we define typically is something which is called as quality, which is also called as the dryness fraction. So, this dryness fraction is defined as the fraction of this mixture which is in the vapor phase. So, over here I have some amount of mass in vapor, some amount of mass in liquid. So, the dryness fraction is the fraction which is in the vapor phase. So, it is essentially the mass of the vapor divided by the mass of the vapor plus the mass of the liquid. So, this is how we define the dryness fraction. We usually denote it by the alphabet x. What you will recall is we have used x earlier to represent mole fractions in the case of ideal gases. That is a different thing, and this is a totally different thing. You should make sure you do not get mixed up between the two. In the case of ideal gases, we said x is the number of moles of the gas divided by total number of moles. Here we are using x to say it is the mass of the vapor by mass of vapor plus mass of liquid. So, they are very different things, but the contexts are quite different. So, I am sure you will not have trouble remembering them. So, in general, we use the alphabet F to represent liquid, it is fluid, and G to represent gas, which is vapor. This is traditionally the notation used in all the books. So, what we said as mass of vapor is represented as mg, the mass of liquid is represented as m subscript f. So, the total mass is mf plus mg. So, the total volume is the volume of the liquid plus the volume of the vapor. So, that is Vf, F represents liquid, fluid, and G represents the gas. So, V is Vf plus Vg. So, that is also something we have, and we also said that x is the quality or the dryness fraction, which is the mass of the vapor divided by the total mass. So, it would be defined in this fashion. We can also get a few other expressions relating these terms. So, what we see is that the total volume is essentially the mass, total mass into the specific volume, average specific volume. So, we can represent this V as m into small v. We can represent this Vf as the mass of the liquid into the specific volume of the liquid, and we can represent this as mass of the vapor into specific volume of the vapor. So, we get this expression over here, and what we can also do is that we can rearrange these things a little bit. So, we have mass of liquid is essentially total mass minus the mass of the vapor. So, I can substitute that for mf here. So, mf is the total mass minus the mass of the vapor into the specific volume of vapor plus mg into specific volume of the vapor. So, I have this here. What I can do is I have this expression now. So, I can divide by m, then I get V is equal to 1 minus, so I am dividing by m here, 1 minus mg by m into Vf plus mg by m into Vg. So, what we see is this is mg by mf plus mg, which is also essentially mg by m, because m is mf plus mg. So, if I do this, I have this here, noting that mg by m is what we call as quality or dryness fraction. What I see is that the specific volume of the mixture is 1 minus x into Vf plus x into Vg, which is an expression which is quite useful for whatever we are going to look at. What we can also write it is, we can also write it in different ways. So, for example, this is Vf minus x into Vf plus x into Vg. This means I can also write this as Vf plus x into Vg minus Vf, which is also another way of writing it. So, I can write it in this way, I can write it in this way. So, this term here represents the difference between the specific volume of the vapor, saturated vapor, and the specific volume of the saturated liquid. So, in the container I have liquid and vapor, both of which are at equilibrium. So, the liquid is saturated liquid, because they can only be at equilibrium if they are at the boiling point. So, therefore, if I have a mixture of both liquid and vapor and they are at equilibrium, they must be at the boiling point. So, the liquid is what I would call a saturated liquid, the vapor is what I would call a saturated vapor. And if I was to look at, for example, the TV diagram, I have this liquid vapor dome, I have an isobar here, for example. So, the liquid must be at this condition and the vapor must be at this condition. So, the specific volume of the liquid is whatever would be corresponding to this, the specific volume of the vapor is whatever would be corresponding to this. So, this is Vg and this is Vf, and this Vg minus Vf is what we often write as Vfg. It is essentially the change in specific volume as it goes from liquid state to vapor state at that saturated condition. So, I have this the same thing written in 3 different ways. We can use either of them depending on what is convenient for us when we look at some problems in this area. The saturated vapor here is sometimes also called dry saturated vapor, to emphasize that the quality or dryness fraction at this point is 1. So, if I had vapor all of which is at this point, if I had, then what I would see is, for example, if I had a container having only vapor at the saturated condition, then x would be mg, which is the mass of this gas, divided by mg plus mass of liquid. Let us say all the liquid just became vapor, then the mass of liquid is 0. So, it would be 1. So, to emphasize that x is 1 in cases of like this where x is really 1, we call this as dry saturated vapor. What you should keep in mind is, I have assumed here that I had liquid and vapor, the liquid has just become vapor. So, it is on this line. If I heated this further, then it would become superheated vapor. Then this we do not talk of the quality any longer when the vapor is superheated. We talk of quality only when we are at the saturated condition, which means we are either at this line or in between or at this line. Only in those cases we talk with quality. To the left of it we are completely in liquid, to the right of it we are in superheated vapor, and we do not talk of the quality anymore. So, this brings us to what are called as steam tables, where from which we can find out properties of the substances which we want to use. If we are using water, we call this as steam tables. If we are using, for example, other substances like other refrigerants, we have tables for those. If we are using air, we have air tables, we have nitrogen, we have tables for nitrogen, and so on. So, as part of this course, we are going to look at steam tables, and we are also going to look at tables for refrigerants which are used in refrigerators, one of which is R134A. What we will maybe do is look at the steam tables right now, and we will look at the 134A tables a little later on. So, the top portion over here, it says properties of saturated water and it says temperature table. So, the important thing to note here is this is properties of saturated water. So, saturated water means that it is either on the liquid line or in between the liquid and the vapor line or on the vapor line. So, we are only looking at those region. We are not looking at compressed or subcooled liquid. We are not looking at superheated vapor in this table. So, we are only looking at this region in this table. So, this is it says temperature table because this is listed by temperature. So, if I was to go to the next page, the previous page here on page 1, I have properties of saturated water and it says pressure table. So, in page 1 here I have the same data as on page 2, but this is listed by pressure, whereas in the next page I have saturated water tables listed by temperature. So, let me for example look at the pressure table first. So, in the pressure table my first column here lists the pressure. The units are megapascals, which means it is 10 power 6 pascals. The temperature is listed in degrees centigrade. I have the specific volume. Vf represents my specific volume of saturated liquid, that is listed in meter cube per kg. 1 by that Vf would give me the density. Vg represents the specific volume of saturated vapor, which is the vapor on the saturated vapor line, that is also listed in meter cube per kg. Uf represents energy of the saturated liquid, it is per kg. There is a specific property again listed in kilojoules per kg. Ug is the same thing for the saturated vapor line, which is also listed. So, for example, I have on a TV diagram this dome over here. So, if I was to take some reading over here, let us say I was to look at this value here, where the pressure is 0.1 megapascal. So, 0.1 megapascal is essentially 0.1 megapascal is essentially 1 bar, so, or 100 kilopascal. So, I can draw for example a 1 bar isotherm over here. This would be, let us say, a 1 bar isotherm. What it says is that at a pressure of 1 bar, the saturation temperature is 99.6 degrees centigrade. So, over here the temperature can be some value, but when I reach this line, when I reach the red line over here, at the intersection point over here, the temperature is 99.6 degrees centigrade. So, if I draw an isotherm, which is just a horizontal line on a TV diagram, this isotherm has a temperature of 99.6 degrees centigrade. So, for this condition, the specific volume is 0.001043 at the saturated liquid condition. So, this volume is this value. At the vapor state, the volume is 1.694 meter cube per kg. So, which means here it is 1.694 meter cube per kg. Corresponding to this point, which is what we call as F, this point is what we call as G. So, corresponding to this point F, the internal energy is 417.4 kilojoule per kg. Corresponding to this point F, it is 2505 kilojoule per kg. The enthalpy at this point F is given as 417. The enthalpy, the point G, which is this over here, is given as 2674.9, which is the enthalpy at this point G over here. The difference in enthalpy between G and F, so difference in enthalpy between here and here is listed in this table as HFG. So, this HFG is given as 2257.4. So, the HFG, as you remember, is the difference between the enthalpy at the vapor phase and the enthalpy at the liquid phase when the phase transition happens, which is essentially what we call as the latent heat of vaporization. So, we see that the latent heat of vaporization in this case is 2257.4 kilojoule per kg. So, that represents the amount of heat we need to give to go from the state F to the state G at a pressure of 1 bar. because we are looking at a pressure of 1 bar or 0.1 megapascal. So, that is essentially what we need, and we see the last 3 columns represent entropy. Since we haven't looked at what entropy is, we will come back to these last 3 columns a little later on in the course. So, for the time being, we are going to confine ourselves to this portion of this graph. What we can also see is, if I was to look at some other condition, let us say I was to look at 0.2 bar, which I am going to mark here, sorry 0.2 megapascal, which is essentially 2 bar. The boiling temperature at 2 bar is 120.2 degrees centigrade for water. So, if I was to look at a 2 bar isobar, let us say it is somewhere like this. So, the temperature on this line is 120.2 degrees centigrade. So, corresponding to this point over here, the volume is 0.001061 meter cube per kg. Corresponding to the vapor point is 0.8857. So, this point has a volume of 0.8857. We can see that is lower than this. We can see this is higher than this is lower than this. The internal energy is higher than this case. So, we are now looking at this case. So, we are looking at these values. The internal energy is higher compared to this. Internal energy of the vapor is also higher. Internal energy of vapor is higher here because the temperatures are higher. The enthalpy of the liquid at the boiling point, pure liquid at the saturation condition at the boiling point is higher than it was, and it is also higher for the vapor. So, the vapor at this point has a higher enthalpy than the vapor at this point. The liquid over here has a higher enthalpy than it had at this point. But what is interesting is, if we look at the change or essentially the latent heat, we can see that the latent heat was 2257 at 100 degrees centigrade. The latent heat has come down to 2200 kilojoule per kg as we go to a higher temperature of 120 degrees and a higher pressure of 2 bar. So, we see that the latent heat is coming down as we go to higher pressures and temperatures. So, this lists the values at different pressures. The question is, what do we think would be the last pressure on this? So, we have already discussed that in some sense. So, the last value on this must be the value at which you can no longer have any difference between the liquid and the vapor, and we know that that point is what we call as a critical point. So, the last value here is for the critical point where the pressure is 22.064 megapascal, so essentially 220 bar. The temperature is 373 degrees centigrade. We see that the specific volume of the liquid and the specific volume of the gas are the same. We see that we can either consider it all as liquid, all as gas, or any fraction of it as liquid and the gas, it does not matter, the specific volume is the same. Similarly, the specific internal energy of the liquid and the vapor is the same. The specific enthalpy of the liquid and the vapor is the same, and the difference in enthalpy between liquid and vapor is essentially 0. So, we see that the latent heat becomes 0 at the critical point, which is what we expected. So, this is something we can see from this data table. So far we have been looking at this table where we are looking at properties of saturated water, and the pressure table where these values are listed by pressure. Let us go on to the next page of this file where we have the same properties of saturated water, only thing is they are listed by temperature. So, they are listed here for convenience by temperature or pressure. We can look at either of them. So, the previous one was listed, if you were to look at page 1, these were listed for example in these cases at intervals of say 0.0002 megapascals, and then over here in terms of say 0.001 megapascal, and then later on at 0.02 megapascals and so on. So, we have them listed at different ranges of pressures. In the next table we see that they are listed at every 5 degree change in temperature. So, depending on whether we are looking for pressure, whether we know the pressure values or the temperature values, it may be more convenient to look at either of these tables. The values in between which are not here, for example, if I wanted a value at 22 degrees, I could always interpolate either from this or from the previous table, it would not matter which, I can interpolate and get these values. So, like in the previous case, we have over here temperature in degrees centigrade, pressure in megapascals, specific volume at saturated liquid and saturated vapor line in meter cube per kg, energies, specific internal energies of the liquid and vapor, specific enthalpies of liquid and vapor, and in between over here we have the latent heat, and we have entropy values which we are going to look at later, and we have the same we can draw the same graph as before. So, we have on a TV diagram, we can have for example isobars. So, over here we have things listed by temperature. So, for example, if I was to look at a temperature of say 20 degrees centigrade, so let us say this is 20 degrees centigrade, then the saturation pressure is 0.002339 megapascal. So, which means it is 0.023 bar, or essentially if I take 1, 2, 3, 4, 5, 6, then I see that is 2339 pascals. So, that is the boiling pressure. If I wanted to boil water at 20 degrees centigrade, I can boil water at 20 degrees centigrade if I brought the pressure down to this value. Then the liquid would have a volume of 0.001002. So, I am essentially looking at this row over here. This would be the volume of the liquid, this would be the volume of the vapor, the internal energy would be this for the liquid and this for the vapor, and the enthalpy would be 83 at this point, it would be 2537 at this point, and the difference in enthalpy between the vapor and the liquid, which is our latent heat, would be this value. So, I would need to give 2453 joules, sorry, this is kilojoules per kg of liquid in order to convert it into steam at this temperature and pressure. Whereas, if I wanted to convert the same thing at 100 degrees centigrade, which is here, I would only need 2200 kilojoules to convert 1 kg of liquid water at 100 degrees centigrade into 1 kg of steam at 100 degrees centigrade at a pressure of 0.1014 bar, sorry, megapascals, 1.014 bar. And like in the previous case, what we can see is if we come down to the bottom, so I can do this process at other temperatures, and the last temperature value here corresponds to the critical point, which is 373.95 degrees centigrade and a pressure of about 220 bar or 22.06 megapascal. The specific volume of the water in liquid form and vapor form is the same. The specific internal energy in liquid and vapor is the same. Specific enthalpy for liquid and vapor is the same, and the difference, which is HFG, is 0. And similarly, we see values for entropy as well. So, we can use this to find out properties of liquid water at saturation and properties of vapor at saturation, and we can also find out properties of mixtures. Knowing the liquid and vapor properties at saturation, we can find out properties of mixtures, and we can see that this says it has properties of superheated water. So, essentially this deals with properties of water vapor in the superheated form, and it has a lot of values over here. So, we have here, for example, on this page we have 1, 2, 3, 4, 5 into 3, 15 tables, 15 small tables, each of these is a small table. And if we look at the next page, we have again several more small tables, we have another 18 small tables on this page. So, they have properties at different conditions. So, we look at one of them in a lot of detail, and then the rest of them are similar to read. So, let us look at, for example, on page 3, this table on top. So, the first thing which says on top is what is the pressure, and in bracket it says what is the saturation temperature at that pressure. So, for example, we are looking at only water, we are looking at superheated water. So, if we had water at 0.01 megapascal or 0.1 bar, if the temperature was 45.8, it would be saturated. So, that is the saturation condition, that is the boiling point. 0.01 and 45.8 together is a boiling point. Of course, you can have some other boiling point, 0.05 and 81.3 is also a boiling point. Each combination of these is one boiling point, but for this pressure, this is the boiling point. So, at this pressure, if you had a temperature less than this, it would be in liquid state. So, we will not have those properties here. If for this pressure, if it is at this condition, then we should look at the previous tables which had properties of saturated liquid. So, we only use these tables if for this pressure we are looking at a temperature greater than this saturation condition. So, for these cases, if I have, for example, this pressure and I have temperature 50 degrees centigrade, I know that 45 is the boiling point. So, at 50 degrees it is vapor. So, because it is completely vapor, there are no question of listing out properties of liquid. So, I do not have any properties of liquids in this table. I have the volume of this vapor, I have the energy of the vapor, I have the enthalpy and the entropy of the vapor. So, this first tells me that what is the value at saturation. So, saturation here corresponds to 45.8. So, at 45.8 degrees centigrade, the specific volume is 14.67, the energy is 2437.2 and the enthalpy is 2583.9. If I go to a higher temperature of 50 degrees, this is the volume, this is the energy, this is the enthalpy. As I go to higher and higher temperatures, I can see this is the volume, this is the energy, this is the enthalpy at 300 degrees centigrade. At 600, this are the corresponding values of volume, energy and enthalpy and so on. Similarly, if I go to some other table, let us say I go on to this, let me see for example this table over here. Let us see this table. Over here the pressure is 0.1 megapascal, which is 1 bar. The corresponding boiling point is 99.6 degrees centigrade. So, at 99.6, which is the saturation temperature, the volume is 1.64694 meter cube per kg, which is also the same value which we saw from the saturated tables, because this has to correspond to the saturation condition. So, in all of these, the topmost value, which is saturation condition, is the same thing which you would have seen in the saturated table also. At 50 degree, there is no value here, because 50 is lower than the saturation. So, you cannot have superheated water at this pressure at 50 degrees centigrade. So, there is no values given here. At 100 degrees, which is slightly above the saturation condition, these are the volume, energy and enthalpy values. At 150, this is the value, at 200, this is the value and so on. The values are given up to say 1000 here. At 1000 degrees, these are the values. We could have values for higher temperatures also. This table does not give it, because we do not usually use values beyond those. So, similarly, if I went to some other condition over here, I am going on to the next page, on page 4. I have similar values. So, let us say on page 4, I pick this condition over here. So, this gives me the values for steam at a pressure of 15 megapascals or 150 bar. So, at 15 megapascals, the saturation condition is 342 degrees centigrade. So, if I want to have a mixture of water and steam at equilibrium at 15 megapascal, it needs to be at 342.16 degrees centigrade. So, at that condition, so at 342.16 degrees centigrade, the volume would be this, the internal energy would be this, the enthalpy would be this. At the same pressure, if I wanted to know what is the value at 500 degrees centigrade, so at 15 megapascal and 500 degrees centigrade, my specific volume would be 0.02 meter cube per kg, energy would be about 2998 kilojoule per kg, enthalpy is about 3310 kilojoule per kg, and we have entropy, which we will look at later. So, essentially this gives us properties in this fashion, and using this we should be able to find out properties of different substances and use them for any calculations which we need. Thank you.